All right, so let's get started. In the morning lecture, we had an introduction to the basic cosmological theory that we will be using to study cosmology. This was the hot Big Bang framework within general relativity. Okay, and we looked at distances, redshift, and saw pictures of the cosmic web and the cosmic microwave background. So, in this lecture, what I will do is to discuss what is currently called the standard model of cosmology. And what we want to do is to understand its components and what these components are telling us about what the universe behaves like, what it was doing in the past, what it might do in the future. And more importantly, we would like to also understand why we are saying that these are the particular components and in these particular proportions. So I will also give you an overview of the observational constraints on these components. Okay, so right. So our universe, the best that we understand it today, is comprised of these few different components, and this is a pie chart, as you can see. And the stuff that we are made of, which comprises of electrons, protons, and other elementary particles, this a cosmologist would call baryons. Okay, so all the atoms, molecules, etc., that you're familiar with, will be clubbed together as baryons, and that forms a relatively small fraction of the total pie chart budget. The radiation which we were discussing, cosmic microwave background, which was, as I mentioned, an extremely important observational piece of evidence in favor of this model, that forms today such a small fraction of the energy density budget that it does not even show up on this particular plot. Okay, in order to see it, you have to go back well into the past. So this is another version of the same pie chart. This is the version that was seen today in the other slide. And this is the version as it would look like in the past. Because as you know, the energy densities of these different components behave differently with time. So if you go back to when the universe was around 380,000 years old, we'll see why this epoch is interesting in a few slides from now. At that time, you can see there is a substantial chunk made up by photons and neutrinos. Atoms are still small, but they are significant. And then there's a large chunk made up of dark matter. And this dark matter is again forming a large chunk today. In particular, this is cold dark matter, and we will see what this means and why we are saying it is cold and dark. But then there is this mysterious component, like I said, dark energy, or for most, based on whatever evidence we have today, it looks very much like a cosmological constant. And in terms of the energy budget, it makes up a substantial chunk, almost 75%, 70 to 75% of the total energy budget. So as you can see, all of these components are typically referred to in terms of the values of their omegas. So remember from the previous lecture that an omega for a particular energy or matter component is defined by the energy density of that component divided by the critical energy density of the universe. Critical energy density is given in terms of the Hubble parameter and Newton's constant. Okay, so this is the overall picture that we think is describing the universe well today. So let's go into a few details and see how this emerges and happens. Okay, so this is again just in words the standard model of cosmology. It contains these few species. Excuse me, just one second. All right. So now if I look at the Friedmann equation, remember the Friedmann equation wrote down the Hubble parameter squared in terms of a sum over energy densities in the universe. Okay, so now the energy densities, like I said, you can divide out by the critical density and write things in terms of omegas. But critical density is nothing but the square of the Hubble parameter with the Newton's constant thrown in. So if I divide by the critical density on the right hand side of Friedmann's equation, on the left hand side, I'm basically dividing by a Hubble parameter, or in this way of writing it, I'm dividing by the Hubble constant squared, which is the value of the Hubble parameter today. So in order to do this, I will divide by critical density today And then these omegas with the subscript zeros, they are all defined at current epoch. Okay, and Friedman's equation, of course, is a time dependent equation. So the right hand side contains energy densities, which are functions of time. But we know how these functions of time behave in terms of a simpler variable like the scale factor or the redshift. Okay, and remember, scale factor and redshift are also related to each other. This is one of the first things we saw. So what will happen here is that the radiation, which remember behaves like 1 over a to the power 4, will have a 1 plus z to the power 4 dependence here. Similarly, non-relativistic matter, which comprises not only of the cold dark matter component, but also ordinary baryons, which are non-relativistic throughout most of history, this will pick up a 1 plus z cubed or a 1 over a cubed dependence. The curvature term was 1 over a squared, so it has a 1 plus z squared. And the cosmological constant term is a constant, so it just has a constant here. And this h naught, okay, so the reason I'm writing these is because these numbers, omega r0, omega m0, omega lambda 0, omega k0, omega b0, and h0 itself, these form some of the parameters of the standard model of cosmology. So these are parameters in the sense that the equations don't care what their values are. The equations only care that if the value is non-zero, for example, then there'll be a 1 plus z to the 4 if omega r0 is non-zero, and similarly for the others. But the values are interesting values because they are telling you something about the universe that you live in. So just like Newton's constant has some value, the electron mass has some value. In the same way, h naught has some value, omega r naught has some value. So these are, if you believe the model, then these are fundamental constants, and then you have to ask what their values are. Of course, this is in the context of this particular model. If I choose to describe the universe using a different model of cosmology, then I will have different parameters. So, in that sense, you don't really always treat these at the same level as Newton's constant, but they are still very, very interesting constants whose values you would like to know within the framework of this standard model. H naught usually is, remember, it has units of inverse time. Historically, because of the way Hubble first used it, its units are reported in kilometers per second per megaparsec. It's very easy to understand. What Hubble did was he took observed redshifts and multiplied them with the speed of light. So he got something that is CZ, which he called a velocity, and he measured that in kilometers per second, and he put that on the vertical axis. On the horizontal axis, he put distances in megaparsec. So obviously, if you put a straight line through this graph, you will get a slope which has units of kilometers per second per megaparsec. So that is what is done here. And the uncertainty in the Hubble parameter is captured by this dimensionless number, little h, whose value now you have to go out and determine. So typical studies at present return values that are of order unity, specifically little h is of order 0.7. Okay, so this is the setup for the standard model. And before I go into a detailed description of the observations which give us all of these values, there is one important piece of physics that we would like to understand, which will teach us something about the cosmic microwave background and its connection to large scale structure today. Okay, and all of it happens in the framework of this cosmological model. So let's see this a little bit first. So this is a discussion of the thermal history of the universe, and in particular, what was called the photon baryon plasma. Okay, so thermal history of the universe. Actually, if you look at a book like Paddy's book or Narlikar's book, or there is a entire book dedicated to the early universe by Kolb and Turner. So you will see that it's a very rich subject with a lot of different technical details, small things which are very interesting in their own right. And moreover, this whole field made extremely important early predictions for measuring the abundances of nuclei produced primordially. So this is called Big Bang nucleosynthesis, the entire theory. And these predictions were very successful, as I will show in a few slides from now. I will not have time to discuss any of this. So instead of giving you such a detailed description, I've chosen to give you a one-slide summary. It will not do justice to the topic by far, but I hope it will get you interested in at least going back and reading about it. Okay. So what is the situation we are talking about? Remember, the standard model of cosmology says that the early universe was hot and dense and expanding. Because it is expanding, the temperature is going down. Okay, so the expanding universe cools. In such a universe, there are different kinds of species available. There are maybe at very high temperatures, for example, there will be free electrons, free protons, free neutrons. There may be other species like neutrinos, and everything is interacting with photons, and everything is also interacting with gravity. Okay, so this is a cartoon picture adapted from Dordelson of a relatively late phase in the universe when only electrons and protons were available from the baryonic species, but photons were there, gravity is there, so you can see using these arrows which species interacts with what. And there is presumably also dark matter. We will see what the evidence is for dark matter later. But the idea of dark matter is that it doesn't interact with photons, that's why it's dark, and it doesn't interact with electrons and protons either. However, it has mass, so it interacts with gravity. Okay, or rather, it interacts with other species through gravity. Photons and electrons can interact with each other through Compton scattering. Electrons and protons can interact with each other through Coulomb scattering. So all of this means that these kind of interactions, if they are happening very, very fast, for example, okay, so if my densities are high enough that there are enough electrons and protons and photons available in a small volume, that many, many interactions can happen per second. So more precisely, if enough number of interactions happen per second compared to the rate of expansion of the universe, compared to the time over which the universe doubles its size, then these interactions will come into thermal equilibrium. Okay? So once interactions like this, like if Coulomb scattering is in thermal equilibrium and if Compton scattering is in thermal equilibrium, these species are in equilibrium with each other, and you can use equilibrium thermodynamics to describe their abundances in the presence of a temperature for the full bath, which is a decreasing function of time. Okay, because the temperature of the bath, remember, it has to change. It is changing because the universe is expanding and the volume is increasing, and this plasma is cooling. And you can show that for most of the interesting history of the universe, the behavior of temperature with the scale factor is basically 1 over A. And this is again easy to understand if you remember the redshifting of the photons. The photon energies, they decay like 1 over A, and the temperature of a black body is very intimately connected to the typical energies of the photons that it is describing. Okay, so this is why the temperature also decays like 1 over A. All right. So this is the situation in the early universe during equilibrium. Other things can happen, which I will not go into, but it is just for your knowledge, or you should know that species which are in equilibrium, for example, electrons and positrons. Okay, so electrons and positrons can annihilate with each other to produce photons, and high enough energy photons can also pair produce. Yeah, and then electrons and positrons can have scattering interactions with other charged species as well. So such species which are capable of annihilations, if they become non-relativistic as the universe is expanding, and if these annihilating interactions remain in equilibrium, then these species will keep annihilating and they are becoming non-relativistic, which means that the temperature of the bath at that time is much smaller than the masses of these species measured in appropriate natural units. So if this is the case, then imagine what a annihilation reaction looks like, right? Electron and positron annihilate and create two photons. The reverse reaction of pair production requires two photons to come together and become an electron and a positron, create an electron and positron. This can only happen if the photons have high enough energies, right? Because electron has a rest mass of half an MeV. Positron also has a similar rest mass. Then the photons that you require should have energies of order 1 MeV or so in order to successfully pair create. So if the photon temperature of the bath has fallen substantially below 1 MeV, then there will not be enough high energy photons available to create pairs of these particles. So the annihilation reaction has no problem in happening, because if the densities are high enough, then electrons and positrons will meet each other and annihilate. But the pair production reaction will not happen. So as a result, this becomes a one-way process, and these annihilations, they simply deplete the number of these some of these species, such as positrons. Okay, so in such cases, for a brief period of time, the photon temperature will depart from its 1 over A behavior because the entropy contained in these annihilating species will be transferred to the relativistic bath through the excess photons that are being created. All right, so this is just a very, very quick introduction to things that happened during thermal history. I will not discuss this further. What I will talk about is the photon baryon fluid. Okay, so this fluid, because these interactions, Compton scattering, Coulomb scattering, are in thermal equilibrium, although electrons and protons are themselves, although electrons and protons are themselves non-relativistic at the temperatures, at let's say temperatures of substantially less than 1 MeV, uh, the fact that they are tightly coupled to photons means that this whole bath of photons, electrons, and positrons, it behaves like a relativistic fluid. Okay, because photons are there and they are just flying around at speed of light everywhere, but they are tightly coupled to electrons and protons. So, as a bulk, this whole plasma behaves like a relativistic fluid. And this fluid supports sound waves. And the speed of sound in these waves is approximately c over root 3, which you may have come across in your statistical mechanics courses. All right, so that is a very interesting and important fact to keep in mind about this epoch, that the photon baryon fluid supports sound waves. And these sound waves, starting from very, very early times, if you ask the question, suppose I take, I'm a drummer, cosmic drummer, and I ping my drum, a cosmic drum, which is this photon baryon fluid, very close to the Big Bang, just a little bit after the Big Bang. How long will the sound waves propagate? So basically, they will propagate as long as the photon baryon fluid can support these sound waves. So how long does that happen? It turns out that these sound waves can be supported until roughly 400,000 years after the Big Bang, 384,000 to be precise. And why is this number, where does this number come from? This number comes from asking what happens to the reaction in which an electron and a proton combine to form neutral hydrogen and a photon. And on the other side, a neutral hydrogen atom is hit by a high energy photon and is ionized, and it converts into electron plus proton. Okay, so on one side of this reaction, you have two charged species, electrons and protons, both of them are charged. On the other side of the reaction, you have one neutral species and a photon, hydrogen and a photon. Okay, so now there is a rate at which this reaction is occurring. And what I said earlier is that any reaction in this epoch will remain in thermal equilibrium until its reaction rate falls below the Hubble expansion rate. So now at some point, in fact around 400,000 years after the Big Bang, the reaction rates for these reactions, because these reaction rates depend not only on the reaction cross section but also on the number density of free electrons available. Okay, so the number densities, remember, will be diluting as 1 over a cubed, and the reaction cross section is something, and the velocities will behave like something. So these reaction rates are going to be a function of time, and eventually the value of this reaction rate falls below the Hubble expansion rate, which means that the reaction which is creating a hydrogen atom out of photons, this reaction will be allowed, but not enough high energy photons are available to ionize a neutral hydrogen atom and convert it into electrons and protons. Okay, fine. So lots of neutral hydrogen atoms are being produced around this time. Yeah, but what does this mean for the photons? Photons, remember, are only coupled through this fluid mainly through Compton scattering with electrons. Little bit through protons also, but protons are very massive. So photons really don't effectively couple to protons. Photons effectively couple only to electrons, through Compton scattering. But now all the electrons are getting eaten up by hydrogen atoms, right? Because electrons and protons are coming together, forming a hydrogen, no electron left anymore. So if enough hydrogen atoms form and not enough hydrogen atoms are ionized, the number density of free electrons starts falling very dramatically. This means that the Compton scattering reaction that is keeping the photons coupled to electrons becomes very ineffective now, because the photons are not seeing any charged particles anymore. And if you remember your standard model physics, photons only interact with charged species. They don't interact with neutral species like neutrons, and they don't interact with the hydrogen atom directly. Okay, so because of this, as hydrogen forms in the universe, neutral hydrogen, the universe slowly becomes transparent to the presence of photons. Okay, so the photons simply do not see anything anymore, and they start free streaming. So a photon which is traveling in a line, it may have interacted with an electron at some point and scattered off and moved in a different direction with a different energy and etc. But now, if that electron has been eaten up by a hydrogen atom, even if the hydrogen atom is in the same physical location, this photon will effectively not see the hydrogen, just pass through, because the hydrogen is not overall charged. So these photons, they free stream, and they will basically keep going as long as they can go, okay, at the speed of light. They will keep going in all possible, whichever direction they have picked, they will just keep going in that direction. The universe is expanding, so these photons, although their directions don't change typically, their energies will decay like 1 over the scale factor. And eventually, these photons coming from all possible directions, if I am sitting at a particular place, I will see them, right? I can collect them in a like the radio antenna, for example, and I will detect them. This is what comprises the cosmic microwave background. Okay, so this cosmic microwave background is the collection of these photons with the subset of these photons which happen to come to us. There are many other photons which have gone in all possible directions. We have seen only the ones that have come to us. So this is the CMB. Okay, and this epoch at which this happens, it is sufficiently important that there are several names given to it because of the several different interesting physical phenomena that are happening at this time. One is recombination, because neutral hydrogen is forming, it is combining from electrons and protons. The other is photon decoupling. It's again happening around the same time. Once hydrogen forms, the photons decouple from the plasma. Okay, so this is the story of the cosmic microwave background. Now there is something else which is interesting about this epoch, which is that these electrons and protons are also hanging around. Okay, so earlier I said that photons, electrons, and protons, they are forming a fluid with supported sound waves. Now suddenly the photons don't see any charged particles and they free stream. So that means the glue which was holding together this fluid has disappeared now. So these electrons and protons, now they are not part of a relativistic fluid anymore. So they will just gravitate. They are already non-relativistic themselves because the temperature of the fluid was anyway much smaller than their masses. And they are now not even in physical contact with any of these photons because all the electrons and protons are sitting together in hydrogen atoms. So what will happen is the only interactions now that these electrons, protons, or rather the hydrogen atoms will see, that is what the gas will see, is gravity and whatever other gas dynamics is happening. Okay, so whatever gravitational potentials there are at this epoch, around 400,000 years after the Big Bang, these gravitational potentials will start capturing these baryons, electrons, protons, hydrogen, etc. And these baryons will condense into these local potential wells. And eventually, these potential wells will become deep enough that the condensing baryons will start doing interesting things like forming stars and forming galaxies. All right. So, in terms of this crude picture, which I have drawn here, the photon baryon plasma will look something like this, in the sense that there will be sound waves propagating through this plasma, density enhancements and rarefactions. And around 400,000 years after the Big Bang, wherever these density enhancements and rarefactions have reached, they will kind of freeze there because they cannot propagate anymore. So it's like it's like a wave which was propagating and then kind of lost steam and it just stalled over there. But wherever it has stalled, the density enhancements will remain density enhancements and the rarefactions will remain rarefactions. And there locally, you will have condensation of baryons and you will have galaxies, stars, and galaxies forming. So the structure of these at large scales, at 100 MPC scales, because the sound horizon, which is the distance to which sound waves can travel in 400,000 years, this number turns out to be about 100 megaparsec. Okay, so at these 100 megaparsec scales, you should expect that there will be patterns of overdensities and underdensities. not only in the baryonic, not only in the photon temperature distribution because of the free streaming photons, but also in the baryonic distribution traced out by the galaxies. Okay, so that is what I have mentioned here. These freed photons stream to us, maintaining their blackbody spectrum with temperature that falls like 1 over A. Even though these are not in equilibrium, you can prove mathematically that the structure of their distribution function does not change. It remains a blackbody form. The only thing that happens is that the temperature falls like 1 over A. And they become the cosmic microwave background with a temperature which becomes 2.7 Kelvin on average today, and with tiny density fluctuations, which are the remnants of these acoustic waves that were present in the photon baryon plasma at that time. Okay, so that's the CMB. Correspondingly, these baryons eventually form galaxies, and the same remnants of the acoustic correlations, which are seen as CMB anisotropies, they will be imprinted in the number density of these galaxies as a function of space. And they are called baryon acoustic oscillations. So in the literature, you will see the acronyms CMB and BAO very frequently. And this slide is telling you what these acronyms mean and where they come from. Okay, so I will not discuss this anymore. If you have questions, you can ask me later. Okay, so let's move on now to discussing the various components of the standard model. So let's talk about radiation first. We have already discussed this in some detail now. So remember from your basic physics that the energy density of a black body spectrum of radiation is given by 4 sigma over c t to the power 4, sigma being the Stefan Boltzmann constant. So if I know the temperature that I measured today, I can write down the energy density as well. Okay, and this is a Nobel Prize winning experiment from the same Kobe satellite which discovered the fluctuations in the microwave background. There is a I will ignore the chat for now. There is a measurement of the spectrum of these photons, which comprise the CMB. And the interesting thing about the spectrum, first of all, you can see that the black line and the data points agree extremely well with each other. The black line is a black body with a temperature of this 2.72548 Kelvin. The data points with error bars are the measurements of the spectrum using the FIRAS instrument, okay, on the Kobe satellite. But the really interesting part of this plot is the size of the error bars. So look at what has been plotted here. It says 400 sigma error bars, which means that usually I would plot data measurement by saying I have a value of y and a delta y which I associate with it. And this delta y gives me the typical uncertainty over which y will fluctuate. Here, the uncertainties are so tiny that they have to be multiplied by a factor of 400 just so that you can see them on this plot. So in other words, if I actually think about the level of precision with which this spectrum is obeying a black body form, it is the most precise black body known to human beings. Nothing in the lab can come close to this. Okay, and the universe produces this essentially perfect black body. Having said that, there are small departures of this black body, and that is a whole set of, it is a whole topic of research on its own. It's called spectral distortions. And these spectral distortions come in various forms, and each of these forms tells us something interesting about the universe. So we currently actually at IUCAA don't have anybody working on spectral distortions. So at the end, if you're interested, I can answer as many questions as I can, but I will also refer you to other people in the country who are working on these things. Okay, so this is as far as the spectrum of the black body of the cosmic microwave background is concerned. And once you know the temperature of the spectrum, you can calculate its energy density. In SI units, it turns out to be this, okay, in CGS units. And if you compare it with the critical density of the universe at current epoch, remember the critical density is completely determined by the Hubble constant and Newton's constant. Let's assume that Newton's constant has, for these purposes, essentially no errors. Okay, of course, it has some errors in its measurement, but compared to the errors we are talking about here, the errors in the Newton constant are extremely small. So you can essentially assume that Newton's constant is perfectly known for this discussion. The uncertainties that will arise are due to the value of little h. That has a substantial uncertainty, so it is left just like this. Okay, so h naught is 100 h kilometers per second per megaparsec. So you leave the value of h like this, And then this number is essentially determined by Newton's constant and factors of pi, etc. The temperature of the universe, not of the universe, temperature of the CMB from the Kobe fire ash measurement is this 2.72548 with this error bar. So if I do a simple error propagation, I get a value of rho omega naught to be something with an error of 0.004 in the fourth significant digit. So I can take a ratio of these and I'll get a value of omega gamma, which is the energy density, the dimensionless energy density in photons. Okay, not all of radiation, but in photons. And that will turn out to be this number. So as you can see, it's a very tiny number. And it's happening because the energy density of photons is not a very large number. Its temperature is not very high. Okay, so this is the value of the omega corresponding to radiation. You have to now also remember that there are neutrinos in the picture. So now there is a discussion as to whether you should treat neutrinos as relativistic or not. If neutrinos did not have mass, they would almost certainly be relativistic, and you would then place them as an additional three relativistic species. And then there is a certain calculation that you can do, which will give you a total omega for the radiation species. Now, in reality, the neutrinos have mass because astroparticle experiments have and lab experiments have told us this. So this is not exactly a correct calculation, but for the purposes that we are interested in, this is a reasonable calculation because especially the number that we are talking about is a very small fraction compared to unity. Okay, so this is as far as the radiation energy density is concerned. Now let's look at the energy density in baryons. So as I mentioned a couple of times, there is a whole theory of Big Bang nucleosynthesis, where basically what people did, people like Georg Gamow and his collaborators in the 50s and 60s, what they did was to take this idea of a hot Big Bang very seriously. Okay, and they said, let's study the thermodynamics of this hot Big Bang phase and ask what happens as different reaction species go out of equilibrium and the temperature of the universe falls enough that interesting nuclear reactions can happen and go out of equilibrium. So when you study nuclear reactions, you will find that okay, initially everything is quarks. Okay, then eventually quarks will combine to form protons and neutrons. Eventually, neutrons and protons will combine to form the nuclei of all the chemical elements that you know. So Gamow initially wanted to produce the entire, the entire periodic table like this, but it became very quickly apparent that you will not progress very far because the energy densities of these species, they fall very rapidly as the universe expands. So what you will end up getting is that the first few elements in the periodic table will be formed in abundance, hydrogen and helium in particular, and then some small amounts of deuterium, which is an isotope of hydrogen, and also isotopes of helium. And trace amounts of lithium will also be produced. And higher elements will typically not be produced. They may be produced, but in such small amounts that it is practically not worth considering. However, the amounts of hydrogen, deuterium, helium-4, helium-3, and lithium can be predicted with great precision if you know the value of omega B0. Okay, so everything hinges on the value of omega B0 and the temperature of the universe of the CMB at present time. So at that time, there was a lot of uncertainty in these numbers. But Gamow and collaborators were quite brave and they started making some assumptions about what the CMB temperature might be, and then they made predictions. And in later times, what happened was that the CMB was discovered, its temperature was then known, so some of the uncertainty went away, and then these predictions became very, very tight. So these tight predictions are visualized here. So for example, as a function of baryon density, you can think of this upper axis as this value of omega B0 times little h squared, 0.01, 0.02, 0.05. Okay, and the corresponding baryon density in terms of CGS units is given at the bottom. So what you can do theoretically is to predict what is the mass fraction of each of these primordial species as a function of omega B0. And those are the bands that are seen here. So this green band is for helium-4, the red band is for deuterium, the blue band is for helium-3, and the purple very fat band is for lithium. Okay, and the thicknesses of these bands also tell very interesting stories, which I will not be able to go into here. Where do these uncertainties come from? The thicknesses are proportional to the theoretical uncertainties in these quantities, and each of them has a different origin. Okay, and for example, if you are interested in this, you can look at the book by Kolb and Turner. They give a very nice account of all of these theoretical uncertainties. But the bottom line is, for each of these species, you can make a prediction, and for each of these species, you can try and go and observe the primordial abundance. You may not always be successful in getting the primordial abundance because many of these species are also formed in stars. Thereby hangs another tale. Okay, so the counterpart, so the opponents of the Big Bang model, Fred Hoyle in particular, wanted to produce all of these elements in stars. So Fred Hoyle and company did a detailed set of calculations, which eventually became the theory of stellar nucleosynthesis, as opposed to Big Bang nucleosynthesis. And indeed, many of these elements, most of them, can be produced in stars as well. But the predictions of the Big Bang nucleosynthesis model are very sharp, and they can be compared with certain sets of astrophysical observations very cleanly. So one example in particular is deuterium, which is a very tenuous species. It is very easy to destroy deuterium once it is produced. So in stars, it almost never survives for very long. So if you see traces of deuterium in space anywhere, chances are that it is primordial and it has been hanging around without the formation of stars. So that's why you can see that the squares, the black rectangles, these are observational constraints now on each of these quantities, and you can see that the observational constraints coming from deuterium measurements are the tightest. Okay, but all of the other observations also, with whatever uncertainties they came with, most of the uncertainties come because these species can also be produced in stars. Most of these observations are consistent with a value of omega b0, which is of this order. Okay, 0.0. If I combine all of these numbers, the combined constraint on omega b0 will turn out to be this, dominated by the deuterium constraint. This can be compared with the constraint coming from the analysis of CMB anisotropies, which I will discuss in a second. But basically, I told you that CMB anisotropies are very close to a Gaussian random field. The structure of that Gaussian random field gives us a rich treasure trove of information about these cosmological parameters. Okay, and if you use that information to constrain the same quantity, the number that you get, the mean value, is actually almost the same. Okay, between these two, it's just that the error bars from the CMB now, using the Planck satellite results, are 10 times better than BBN. But you have to remember that the BBN constraints were 30 years or more older than the CMB constraints that Planck satellite is giving us. So this is the status of the baryonic density field. Okay. The next thing, which is the dominant part of the non-relativistic matter today, is what is called cold dark matter. And this is a very interesting story of why we think such a species exists. Historically, what happened was that Fritz Zwicky was looking at optical images of galaxy clusters. So he was studying galaxy clusters, and he tried to get an estimate of the mass of these clusters. And he did it using a very clever technique. It's called the Varial Theorem. So if you remember your Varial Theorem arguments from undergraduate physics, it tells you that a system in kinetic equilibrium due to gravity and random motions will obey the relation 2 times the kinetic energy plus the potential energy is 0. Okay. So Zwicky said, let's assume that galaxy clusters, which are basically collections of galaxies which are gravitationally self-bound to each other, let's assume that these galaxy clusters are in virial equilibrium. So the Varial Theorem will be obeyed. And in such a situation, what you can do is to relate the velocity dispersion, which is forming the kinetic energy term, to the mass and radius of these systems, which will give you a gravitational potential, Gm over R. So M is the total mass of the system, R is the physical size of the system, and the kinetic term will be related to the velocity dispersion. Okay, the square of V squared, the average of V squared. So how do you put these things together? Well, the average of V squared you can try to estimate by using the redshifts of these individual galaxies. Because remember, these galaxies, okay, let's say they are at some cosmic redshift away from you, but then inside the cluster there will be Doppler effects due to the random motions. So if I remove the mean redshift of the cluster for any given cluster, The remaining redshifts that I'm talking about are just random motions along the line of sight. Okay, so I can use that randomness and calculate a velocity dispersion from the redshifts. So I have an estimate of v squared directly from the redshifts. The size of the object I can again figure out because I have the optical image in front of me. So I have an angular size given to me. And I can use a luminosity, an angular diameter distance calculation and say that, these are basically these clusters that Zwicky was using were not very far away. So you can use Hubble's law. So the distance I will know from Hubble's law based on the mean redshift, and the size I will know angular size from the optical images. So I can calculate a physical size for these objects. So now in this equation, I have three unknowns, but two of them I observe. So only one unknown is left, which is the total mass of the system. So I can estimate the mass. Great. I can also estimate the mass by just asking how many stars are there inside each galaxy. So I measure the luminosity of each galaxy, convert it into an equivalent amount of stars, and I ask how heavy are these stars. So under some reasonable assumptions for the mass to light ratios of the stars in these galaxies, what Zwicky pointed out is that he was missing roughly a factor 50 in mass. So if we compare the virial mass estimate to the mass estimate from stars, there was a factor 50 off. The mass estimate from the Varial Theorem was 50 times larger. He labeled this missing mass as dark matter in German, and that name has stuck. Later, once these clusters were understood better, and once X-ray observations started becoming available, what one realized is that the stars are not the only thing. The galaxies are not the only thing that form these clusters. There's a lot of hot gas in these clusters, and the gas is at very high temperatures, and there is a substantial amount of it. So there may have been some hope that, okay, maybe the missing mass that Zwicky was talking about is actually gas, which is not visible in optical wavelengths, but it is visible when you look at the cluster through your X-ray eyes. It turns out that even this is not the final answer because the gas mass estimates also turn out to be at least a factor 10 smaller than the virial mass estimates. So Zwicky's original guess was still true that there is a missing mass and it is not visible. So it is dark. Okay. Eventually, in the 1970s and 80s, people realized by studying, Vera Rubin in particular, realized by studying rotation curves that the standard Newtonian expectation of a rotation curve which should fall off once you go far from a galaxy is not obeyed by disk galaxies which you can trace using their neutral hydrogen emission. Okay, so these rotation curves like this one, for example, remain quite flat, and this then requires you to have considerable amount of mass at these separations from the galactic center. And this mass is obviously not visible in the stars, otherwise you would have seen it. So this is another way of trying to understand trying to see that there is dark matter. And it is again natural to ask, is the dark matter that Zwicky inferred the same as the dark matter that Vera Rubin and later people inferred? Okay, and then there are a couple of other ways of using basically connecting light to mass in order to try and infer how much mass there is. And all of these ways are indicating that there is a dark component to the mass distribution of the universe. The most robust way that we have today of claiming that there is a dark sector to the universe is actually again the cosmic microwave background. The temperature anisotropies of the cosmic microwave background, remember, are of the order of 1 part in 10 to the 5. Today, we see density fluctuations at the same length scales. The length scales are the sound horizon length scales at the decoupling epoch, which, like I said, is 100 MPC co-moving. So at 100 MPC co-moving scales today, we see order unity fluctuations in the density distribution of galaxies around us. Okay, so those 10 to the minus 5 fluctuations of temperature, which is the same as 10 to the minus 5 fluctuations of density of the matter, because baryonic density is related to the photon density and photon density is related to the temperature through T to the power 4. So those density fluctuations of 10 to the minus 5 should have become order unity density fluctuations today, just observationally. This cannot happen in a model of the universe which only has baryons and photons in it. Because the baryons, in order to go from 10 to the minus 5 to 1 today, need to grow more rapidly than they are allowed to grow in the standard model of cosmology. They are allowed to grow only by a factor of 1,000. Okay, because the redshift of the last scattering surface of the recoupling epoch is approximately a redshift of 1,000. So then the amount by which they are allowed to grow is 1,000. The amount by which they have observationally grown is 100,000. So there's a 100-factor discrepancy between the required growth and the allowed growth. The only way you can get around this is by saying that at the time of photon decoupling, when you see 10 to the minus 5 fluctuations in temperature, there must have already been another kind of matter which was not coupled to the photons. And because it was not coupled to the photons, it was not participating in the photon baryon fluid. Because anything that participates in the baryon fluid, photon baryon fluid, will have the same fluctuations as the temperature fluctuations of photons. Okay, so if you did not have, if the species does not couple to the photons, then it would have created its own gravitational potentials by condensing in under its own gravity, and then you can safely allow for this growth that is required. Okay, so that is the way one argues that there must have been a species of matter which does not undergo collisions with photons. There are other reasons to believe that this species should also have been non-relativistic at the time of photon decoupling. Otherwise, the kind of cosmic web that you see today would not have been produced. So this first requirement, that it does not undergo collisions, leads to collisionless nature of dark matter. And the second requirement, that the cosmic web today should look the way it looks, leads to the non-relativistic or cold nature of dark matter. So that's why we believe that there must be a collisionless cold dark matter species in the universe. And the amount of this cold dark matter is then determined by asking for its value of the corresponding omega. And it turns out to be a fraction of 0.3 or so compared to the total one that you require. Okay, and all of these observations also, if you interpret in the same setting, they are all consistent with an omega matter of the order of 0.3. So this is the story of dark matter. And finally, we have the most mysterious of all, the dark energy or the cosmological constant. So I have put up the equation here, which reminds you that this is a species which has a very strange pressure term. It has an equation of state which is P equal to minus rho. So this rho plus 3P is actually negative, and this A double dot term is positive if the only thing dominating the universe is this species. So the current way of understanding this is the cosmological constant. It is not a new idea. It was actually introduced all the way back by Einstein himself. The reasons were very different. Einstein did not like the idea at all of a dynamical universe. He wanted his universe to remain static because that is the way he had grown up. He liked the universe to be not changing. He had his beautiful new equations, which he applied to the whole universe. Almost immediately, he realized that these equations admit dynamically changing solutions for the size of the universe. Not liking this, he introduced a cosmological constant term in his equations, which he had not done until then. And he said that, look, this term is allowed by the symmetries of the equation, so I am going to put it in. Then he said, let's tune the value of this term. Okay, so it is interesting that somebody like Einstein went to such great lengths to do something which today you would argue is not particularly scientific. Right, you are inventing solutions for the problems that you are seeing. So anyway, he did this and he gave a value of lambda. He adjusted the value of lambda and the spatial curvature of the universe in terms of the matter density of the universe in such a way that the universe is precisely poised at being a static universe. It's neither expanding nor contracting. It is precisely static. Later, much later, turned out that this model of the universe is unstable. Even a small perturbation in any of the cosmological parameters that he introduced, either way, will either make the universe fly apart or contract to a black hole. Okay, so this is the kind of model that he constructed using the cosmological constant. And once he recognized, I mean, he was Einstein, of course. So once the observational and theoretical evidence became incontrovertible, he himself discarded the cosmological constant. He said that fine, it was not built. It is not, if this is the way the universe works, then away with the cosmological constant. All right. And then later on, several other people tried to bring back the cosmological constant for other reasons, okay, including Zeldovich, who I will discuss a little bit later. There have been, I've written that it's a tortured history of epicycles. So it kept coming back, going away, kept coming back, etc., several times between the 50s and the 90s. And in the late 90s, one interesting piece of evidence came up, which happened due to supernova cosmography. Okay, so cosmography, remember, is the idea that you can do a Taylor expansion of the distance redshift relation out to not very large redshifts and look for beyond Hubble-Lemaitre kind of terms in the distance redshift relation. In particular, you can look for this Q0 term, which is related to the second derivative of the scale factor. And the way Q0 is defined, there is a minus sign in its definition. So if the value of Q0 is positive, then A double dot will be negative. Okay, so now if you do cosmography using type 1a supernovae, which are standardizable candles, if you're interested in this, let me know later, I can answer questions. Turns out that the value of Q0 is actually negative. So this A double dot that is being inferred is positive. Okay, and this requires your equation of state to be this super strange, less than minus one third. And the cosmological constant actually provides one of the cleanest solutions to this issue. So the and then not just supernova cosmography, but also CMB data, cluster data, etc. All of them are now giving us a consistent picture, which is called this lambda CDM, standard model of cosmology, in which lambda stands for the cosmological constant, in which omega lambda has a value of approximately 0.7, omega matter has a value of approximately 0.3. Okay. So this is the cosmological constant. And finally, there is spatial curvature. How do you detect spatial curvature? It's very interesting. The presence of spatial curvature, remember, changes distances. So there were these expressions for the luminosity and angular diameter distances, dA for angular and L for luminosity. In terms of this function Sk, which if you go back to the previous lecture, you'll see there is this sine or hyperbolic sine of the co-moving distance as a function of redshift. And whether you use the sine function or the hyperbolic sine function depends on the signature of k. If it's positive, you use one. If it's negative, you use the other. Okay. So now what you can do is try to ask, do I have standard rulers in the sky which I can use to test the distance redshift relation, and in particular test the value of the curvature? And the values of curvature are so small typically that you need very, very long lever arms. Okay, so like the sensitivity of your probe has to be very high. So the longest such lever arm that we know of is provided by the angular diameter distance to the last scattering surface of the CMB photons. Last scattering in the sense that CMB photons decoupled, and the last time that they scattered from electrons is the last scattering surface. So that happened at an epoch of 400,000 years after the Big Bang, which is, in terms of photon distance, a certain distance away from us. So you can calculate the angular diameter distance to that surface. This distance now you can try to test by measuring the angular scale of the fluctuations that you expect. So remember the physics of the CMB that I discussed with you? It said that these sound waves that existed in the photon baryon plasma, they can propagate for about 400,000 years at a speed which is about 1 over root 3 of the speed of light. And the corresponding distance, which is called the sound horizon, is a physical length scale in the problem, and its value is around 100 ms. Okay, so this physical length scale now is imprinted in the CMB temperature anisotropy pattern. So what is shown here is a Fourier transform of the CMB anisotropies, and it's the expectation values, the standard deviation of this Fourier transform. And what you can see, the important thing to take away here is that there is a peak at an angular scale which is measurable. Okay, and this peak corresponds to the value physically of the sound horizon at last time. So that 100 MPC scale corresponds in terms of observed angle to a 1 degree scale in the sky. This is an observed scale, and the physical scale coming from theory is 100 MPC. So this is exactly what you need in order to set up an angular diameter distance calculation. So you take your physical scale from theory, you divide it by the measured angular diameter scale from observations, and lo and behold, you have an angular diameter distance. You also know the redshift at which this set of photons was released. It is 400,000 years after the Big Bang, redshift of about 1100. So now I can go and test how much curvature is allowed in the universe in order to explain this set of observations, reconciling with the theoretical knowledge that I know. Okay, so for example, if my k is positive, I would have moved this peak to the left. If my k is negative, I would have moved this peak to the right. It turns out that this k is sitting exactly where it should. So this peak is sitting exactly where k should be very, very close to 0. So look at these numbers, 0.0007, and the errors are at the third decimal place. So the value of omega curvature is completely consistent with being 0. This kind of measurement can also be strengthened further because, like I said, the same acoustic oscillations that you see in the CMB anisotropies are also imprinted in the distribution of galaxies in the sky, which you can measure through what are called Baryon acoustic oscillation correlation function measurements. So if I do that at different redshifts, at different epochs in different surveys, I can use that to strengthen these constraints, and that is also currently being done. Okay, so what the number I've given you actually is a combination of all of these measurements, not only CMB, but also including BAO measurements. And finally, here is a overall picture of what the scale factor of the universe behaves like, or rather the energy density of the universe behaves like in for different components in the standard model, current standard model of cosmology. Okay, so what I have done for this plotting this picture is to take the values of omega matter, omega lambda, omega radiation from what I said before, right? The best fit values, the constrained values that we have before, and omega curvature also I have put in at a value which is a negative value, which is close to the lower edge provided by by these measurements. Okay, so and then I just plugged in the different kinds of energy density species. It's a very simple plot actually, and I have just shown them to you sitting on top of each other. Okay, so the purple curve, this uppermost curve, is the sum of all of them, and the individual species are radiation in blue, non-relativistic matter in green, curvature in this teal, and the cosmological constant, which is this horizontal line at red. So you can see several different interesting things. At very early times, radiation is the dominant species, right? Clearly, because the blue and the purple are almost matching. And this is easy to understand. Radiation behaves like 1 over a to the power 4. So if I make a very small, then very quickly in the past, radiation will become the most dominant species. Then there will be a phase in which radiation cannot compete with matter because matter is falling like 1 over a cube, radiation is falling like 1 over a to the 4. So 1 over a to the 4 will decay faster than 1 over a cube. And at some point in the middle, at this crossing point, this is called the matter radiation equality epoch, the amount of matter now becomes larger than the amount of radiation in terms of energy density. And this phase of the universe is called the matter dominant. This continues for a long time. It's a scale factor on a logarithmic scale until very recently, where this constant value of the cosmological constant, right? It was not doing anything here. It was like many, many, many orders of magnitude below all the other species, but it's patiently waiting until now, finally, it has become larger than the matter energy density as well. And you can see that there is a departure from a fall off, and this energy density is now starting to approach a constant value. Okay, and I've also indicated curvature in this picture, if you believe the standard model, is not really playing much of a dynamical role anymore. And what I've also indicated are the different scalings of the scale factor. Remember, during radiation domination, it would be square root of t. In matter domination, is t to the power 2/3. Both are power law increases. But when you come to cosmological constant domination, you start coming into an exponential increase. Okay, so this is the expansion history of the universe. And finally, in the last few minutes, I want to leave you with a little bit of human history, just building up a little bit on some things that I've touched upon already in the previous lecture and in this lecture as well. So, models of the evolving universe really started in around 1917, right after GR was published. And of course, the first person to discuss this was Einstein, but there was also Willem de Sitter. They were in touch with each other, they were talking to each other, etc. And they came up with very interesting different kinds of models. So, one I have already discussed, matter without motion, right? So, Einstein cooked up this model of the universe, which is precisely static, in which he used the cosmological constant. Willem de Sitter, on the other hand, looked at a very different kind of model in which there is only a cosmological constant. There's nothing else in the universe. This is called the de Sitter universe. And he showed that in the same coordinates as you would use for the FLRW metric usually, this kind of space-time will lead to exponentially expanding universes. So that is the aspect that is highlighted here. Okay, once you reach lambda domination, you will approach a de Sitter universe. Okay, so this is these two gentlemen, Einstein and de Sitter, and in fact later they collaborated and came up with an expanding model of the universe in which there is only non-relativistic matter, and that's called the Einstein de Sitter model of cosmology. But all of that had to wait because Einstein at this time, as I told you, was not at all happy with dynamical models, even though his theory was telling him in his face that such models exist. So these kind of models were explored by Alexander Friedman, a Russian physicist, across the Iron Curtain at the time. So he was working independently. And in 1922, he derived, so he used the Einstein equations and derived what are now called the Friedman equations. And in 1922, he published his first solution to these equations, which he called the closed universe. It's the universe I told you about, where the scale factor expands, stops, and then turns around and collapses again. When this paper was published, Einstein was so against the idea of dynamical universes that he immediately publicly claimed that there is a mistake in Friedman's calculations. Now, I don't know about you, but a young person like Friedman, when he is criticized by the giant that Einstein was and saying that your algebra is wrong, okay, this can be pretty demoralizing. But Friedman was, he was a hardy person, and he convinced a Russian colleague of his to talk to Einstein and convince him that, by going through the paper, that the algebra is actually not wrong, and which happened. And then Einstein also realized that okay, it was too. He was in a bit of a rush, and he had mistakenly claimed that the algebra was wrong. So he published a paper. Einstein published a paper in 1923, retracting his earlier claim that Friedman was wrong, saying that yes, the algebra seems to be correct, but the solutions that are coming out seem to have no physical meaning whatsoever. Okay, it is very difficult to ascribe a physical meaning to these solutions. So you can see that he continues to remain adamantly against the idea of a dynamical universe. This did not stop Friedman. In 1924, he published what was then became the open universe model, just reverse the sign of curvature. And interestingly, this was the same year as Hubble's observations of Cepheids, okay, in Andromeda, so showing that Andromeda is at a cosmic distance away from us. Unfortunately, Friedman died in 1925, 4 years before Hubble's publication of the linear distance redshift relation, and 3 years before Lametre's French paper in which he derived the linear distance redshift relation. So Friedman never lived to see the vindication of his models, and he died extremely young at the age of 37. And finally, we come to Georg Lametre. He, until about 20 years ago or so, was completely an unsung hero. And then voices started bringing out his contributions. And today we understand that his contributions were actually very significant. Already, George Gamow was aware of Lametre's contributions. They were in touch when Lametre was working. But somehow Lametre's contributions got lost in the last few decades. Okay, so it is worth understanding what he did. So during 1924 to 1936, he showed that he was basically a theoretical cosmologist beyond par. Yeah, so in 1927, he wrote a beautiful paper in French, which was therefore not received at all in the West. But in this paper, he constructed a solution of Friedman's equations with non-zero lambda, first of all. Secondly, he derived the linear distance redshift relation theoretically. Okay, he did the Taylor expansions required, and he showed that the linear distance redshift relation emerges from GR as a theoretical prediction. It was an amazing calculation done for the first time. Today, we teach it in cosmology courses as a matter of routine, but this was the first time it was done, and it was a game-changing calculation. He then used in the same paper, he used that linear distance redshift relation to explain the observed redshifts, which later Hubble had also used. So the observations were there. They were Westo-Slipher's redshifts and Hubble's distances. He used the two with proper attribution to Hubble and Westo-Slipher. And he said that you can explain these redshifts in terms of an expanding universe rather than as Doppler shifts. Okay, so he got that right. There is then an interesting history of how the West lost this aspect that he had derived the distance redshift relation. Okay, but that is for another discussion. What is interesting is that in 1931, he constructed yet another solution, which he called the coasting universe, in which, just like Einstein had used lambda to produce a finely tuned static universe, how Lametre constructed a finely tuned lambda for a coasting universe in which the scale factor just keeps. So there is a long static phase, and then the scale factor increases after some time. And at this time, there was a long standing problem with the age of the universe because the age of the universe inferred from the Hubble constant was substantially smaller than the ages of stars in our Milky Way, which does not make any sense. Okay, so Lemaitre came up with a solution for this. He then extrapolated all his solutions to early times and was the first person to come up with this notion of a hot, dense phase in the beginning. And this was the seed of Big Bang cosmology. His views, unfortunately, remained unfashionable well into the 1950s, and he was ridiculed by people like Fred Hoyle. And one of the reasons that he might have been ridiculed is because of his ties to the Christian church, okay, to the Catholic Church. He was a Catholic priest at the time when he was doing all these calculations. Also, isolation, etc., may have exacerbated these things. But for whatever reasons, his views remained very, very unpopular. And another thing was that in 1934, he wrote a paper in which this idea of lambda that he was trying to work with, which he took from Einstein, he suggested that it might arise from vacuum fluctuations, from a quantum field theory kind of calculation. Quantum field theory was not yet developed even. Okay, so it was Feynman and collaborators much later, like in 12 years later, who laid down the rigorous formulation of the required mathematics, which became quantum field theory. But in 1934, Lemaitre was doing pure speculation. But his speculation was right on the dot because later people have been trying to explain lambda as arising due to vacuum fluctuations. And the first rigorous calculation of lambda from vacuum fluctuations was done by Zeldovich in 1968 in using quantum field theory. It turns out that this is a very problematic calculation, and until now we do not have a well-defined solution to it. But all of these things were done by Lemaitre, and therefore it is always worth remembering his contributions. So that is all I have to say. I will stop here and I will take questions. So let me just quickly check the chat and also open the. Okay, so I don't see anything new in the Google sheet. So in the chat, how are potential wells created which attract the baryons? Good question. We will have a little bit of discussion on this. If I do not answer this question in the third or fourth lecture, you please ask me again. Okay, whoever it is, you please, Anudeep, you can ask me again. Yeah. There is some link which has been given to me. I am not going to open links here. So if you have a question, you can raise your hand and ask, but I'm not going to open links. Okay. Okay, there is a question by Vinisha. Please go ahead.
Yes, sir. So when you were talking about the photon baryon plasma, you said about the sound waves. What is the origin or the source of the sound waves?
Origin of the gravitational potential wells. Okay, so since there are two questions, let me quickly answer, and we will discuss this in detail later. Basically, you need some seeds for the perturbations that are visible then as these acoustic perturbations or sound waves. Okay, and these seeds, they, according to the current understanding, they were laid down by quantum phenomena at very, very early times. So there is a phenomenon called inflation, which we will discuss, and quantum effects during the epoch of inflation are what are believed to have been the seeds of these initial density fluctuations. So these density fluctuations are gravitational potential fluctuations, which then couple to matter, and then the matter also picks up these fluctuations. Okay, because gravity and matter are coupled through gravity. So that is the short answer, and the long answer, you please wait. We will see in the upcoming lectures tomorrow. Yes. So, Vinisha, you can please unraise your hand, lower your hand, and Gaurav can ask his question.
Yes, sir. Regarding the previous lecture, sir, what is from where the motivation of the co-moving distances is coming from?
So, the idea, I thought I explained this, right? That maybe you logged off.
Yes, sir. I was having some network issues, sir. Actually, that
Okay, so I can repeat myself. Basically, the idea is the scale factor is telling you that distances in the universe are going to change. Okay, so it is not worth saying, I cannot say something is 1,000 MPC away from us and give it any kind of meaning unless I know unless I have a reference with which I can compare. So co-moving distances give you such a reference. Basically, what you can argue is that let's take 2 points today, and suppose I were able to lay down a ruler between those 2 points and I found that the distance is 100 MPC. Let me define this distance measured today between these 2 points by laying down a ruler, okay, not by light propagation, but by laying down a physical ruler today. The distance that I get, in this case 100 MPC, I will call a co-moving distance. So then, at any other epoch, if I lay down a ruler between the same 2 points, I will get some other value, but that value will be easily predictable based on the epoch at which I'm talking about, because all I need to know is what was the value of the scale factor at that epoch and what is the value of the scale factor at the current epoch. So usually one says that the scale factor of the current epoch, you assume it to be 1, that scaling freedom you have. And then the value of the scale factor at other epochs will directly give you the distance, the geodesic distance between those 2 points. Okay, so that is the notion of co-moving distance, where the distance between 2 points on the metric, according to the metric today, that is called co-moving distance. Physically, the way you might imagine setting up such a set of observers who are at fixed co-moving distance away from each other. These are just labels that you're giving to different observers. This can come from saying that ask for observers who measure the same value of the cosmic microwave background temperature at any given value of time t, and then measure the distances between them, okay, at any given epoch, like today, and call those distances as co-moving distances. Then at any later epoch, all those distances would have changed exactly by the same amount of the scale factor. So then you will again have a set of distances, but they'll be related to the co-moving distance in a very simple way, just by the scale factor. So all of this is in terms of distances defined on the metric. And this is just a useful way of setting up a coordinate system, because now I can label every observer by the value of the co-moving distance from some chosen origin. Okay, and which origin I choose also doesn't matter. I can pick me as the origin, and your distance from me, as at current epoch, I will define as your co-moving distance. Somebody else's distance is their co-moving distance. These are just labels then that I can give to my observers, and I can use it to organize my calculations. Does that answer your question? Is that all right?
yes, sir. Yes, sir. Sir, another thing, sir. Is it because the scale factor is dependent on time? That's why the co-moving distances is defined for different epochs.
Co-moving distance is not defined for different epochs. Co-moving distance is defined as the metric distance at a fixed epoch. The
Okay, sir.
metric distance at different epochs will be different because the scale factor is different at different epochs.
Okay, sir. Okay, sir. Thank you,
And
sir.
metric distance will be related to co-moving distance just by multiplying by the scale factor. That's all. Okay. All right. I don't see any. Okay, here we go. Yes, Dibakar.
So, in one of your slides, where you are showing the omega curvature, interesting, I saw that omega curvature value is less than the error value.
Can it be less than which value? I'm sorry, I cannot hear you properly.
The omega curvature.
Can it be less than which value?
So less than the plus minus value, because the curvature was having omega curvature was having 0.0007, and plus minus value was having more than b. It was having 10
So
decimal
you're
more
asking whether omega curvature can become less than omega matter? Is that what you're asking?
no, no, sir. Can you just open the slide when the last slide where you have shown that omega curvature?
Okay, 1 second. This one.
Yes, sir.
What
Here,
about
here
this?
you can see, sir, the value, the plus minus value is more than the
Yes,
only.
yes. So what is the problem?
So it seems that this is the error in omega curvature, or this is the addition with the total omega.
No,
Total
no, this is an error. See, this is an inferred parameter. So the mean value of the parameter is this, and the error with which you have determined is this. And in this case, the mean value is smaller than the size of the error bar, which is another way of saying that the mean value is consistent with zero, actually. Okay. All right. Let me just take a couple of questions from the chat. Why does CMB follow blackbody spectrum? Yes, very interesting question. So what I discussed earlier was that the physics of these particle interactions is such that all of them are in thermal equilibrium. So then the photons are also in thermal equilibrium, and therefore they are driven towards a blackbody spectrum. Because if you look at the equations governing the distribution function of these photons in equilibrium, you know that the distribution function will approach the blackbody spectrum, right? The Bose-Einstein formula. That is the answer. Is our universe open, closed, or flat? I have shown you evidence that our universe seems to be pretty close to being flat. Okay, and beyond that you cannot say because the error bars are too large. How is normal microwave background, normal microwave radiation different than cosmic microwave? I mean, radiation is radiation. You mean the microwave radiation emitted by your microwaves? It's just that the source is different, and this particular microwave background. Okay, so maybe I can answer it this way. Terrestrial sources of microwave radiation they are produced for specific reasons. So they will produce certain kinds of spectra of radiation of photons. The microwave background spectrum, the microwave part is just a nomenclature to remind you of what the current temperature is. So it so happens that the current peak temperature is in microwave frequencies, but actually the spectrum is it is a blackbody spectrum. So it is not that only microwave frequencies are being emitted. It is mostly microwave are being emitted, but there are all kinds of other frequencies also. Okay, so I hope that answers the question. I think I don't see any raised hands, and there is nothing new in the Google also. Okay, there is a chat. Is it possible to produce CMB in the laboratory? Uh, well, I mean, are you asking, is it possible to produce a black body spectrum in the laboratory? Yes, people produce black body spectra in the laboratory, but not at the level where, not with the precision that you see in the CMB. Okay, you will have spectral distortions there, which are because of errors, impurities in your substances, etc., which are larger than what you see in the CMB. Okay. Okay, so I think it's a good time to stop. Let us end the session and meet tomorrow in the morning. Okay, thank you very much.